Hi all, let's see the next topic of Unit 2, instruction formats and type of instruction formats. So, contents, we are going to discuss about an introduction to an instruction formats and what are the different types of instruction formats that are available. So, coming to the introduction, as we already know, a computer program contains a set of instructions where each and every instruction has a certain format. We call it as an instruction format. So, what is an instruction format? So, an instruction format is nothing but it refers to the layout or structure of a machine language instruction, and it contains several fields and they hold different types of information. So each field in an instruction format, it has a specific role in telling the CPU what is the operation that it has to perform. Where are the operands located? Whether they are located in the memory or they are located in the registers, as well as how to access that particular operand. What is the memory location or a memory address? So what is the address of the register the particular operand resides? So all this information can be specified to the CPU with the help of a instruction format. So if you see the typical components of an instruction format, it mainly contains three fields. As we have already discussed, there are three fields in an instruction format. The first is an opcode, operand, and addressing mode. So opcode refers to the operation that has to be performed by the CPU on the particular data or an operands. So here the opcode can be an addition operation or a subtraction operation, any type of an operation that is specified with the help of an opcode field. Operand is nothing but the data or the addresses which are involved in the operation. So it can be in place of operands, you can directly give a data or an operand value, or you can give an address of the memory location or address of the register where the particular operand resides. That is an operand field. And lastly, the addressing mode. So this addressing mode defines how an operand can be accessed, whether it is a direct address or an indirect address. So depending upon the mode bit, you can identify whether the operand is it a direct address or an indirect address. So if you look at the instruction format, it can be of variable length. There is no fixed instruction format. It is of variable length with multiple number of addresses. So depending upon the number of addresses that are present in the address part of the instruction, it is of a variable length. And these address fields in the instruction format, they vary as per the organization of the registers that are present in the CPU, and it depends upon these formats are supported by the CPU. They depend upon the instruction set architecture implemented by a processor. So there are different types of instruction set architectures that can be implemented to a processor, like RISC, CISC. They are different. So depending upon the type of instruction set architecture, the instruction format size varies. And most of the computers that fall under any one of the three types of CPU organization. So there are three types of CPU organizations called single accumulator organization, general register organization, and stack organization. First, we will see about what are these three types of CPU organization. Coming to a single accumulator organization, all the operations are performed with the implicit accumulator register. So the instruction format of this type of organization, it uses only one address field. So the address part contains only a single address. For example, consider the arithmetic operation, which is addition. So in this case, the contents of the accumulator are added with the contents which are stored in the memory address X. So M of X refers to the address in the memory where the particular operand is stored, and other operand is stored implicitly in the accumulator. So the address field of the particular instruction requires only one address that is used to store the value of the memory location where the second operand resides. So it performs an addition operation on the contents of the accumulator register as well as the operand which is stored at the address specified by m of x, and the result is again stored back into the accumulator. So here x is the operand's address and add instruction results in the operation. So AC is nothing but the accumulator register. So m of x represents the memory word which is located at an address x of the memory. Okay. So this is called as a single accumulator organization. It requires only one address field to hold the operand of to hold the address of one operand, where the other operand implicitly resides in the accumulator. Second type of an organization is a general register organization. So this type of computers, they employ either two or three addresses fields in their instruction format. So you can use a two addresses in the address part. So if you take look at the instruction format of a particular for these type of instructions, they contains the address part of the particular instruction contain either two addresses or three addresses. If you are working on three operands, the address part contains the address of three operands. If you are working with only two operands, the address part contains two operands, addresses of two operands. So each address field specify it can be a processor register or a memory location. So for example, if you see this particular instruction, add r1 comma x. So what we are performing here is an addition operation on the contents of register r1, and x is nothing but the memory location. The word which is stored at the memory location x. This is the location of the memory. So address of the memory where the particular other operand is stored. So it performs addition on the contents of register r1 and the word which is specified at the memory location x. So this is r1, not r. Okay, and the result is again stored at r1. So it requires two address fields. One is the register, one address field to store the r1, and other address field to store the memory address of x. So this is a two address instruction. Similarly, for example, you can take one more example like. So if you look at this example, add of R1, R2, R3, it performs addition on the contents of register R1, R2 and R3, and the result is stored at R1. So this particular instruction, it requires three address fields to store R1, R2 and R3 values. Similarly, you can also represent it another example as R1, R2, comma X. Two operands are the registers and one operand is the memory location. So it performs addition of all the three operands and the result is stored in R1. So this is called as a general register organization. Next is the stack organization. The stack organization uses mainly two instructions. One is push and other is pop. So the instruction push X pushes the word at address X to the top of the stack. So it is called. I think you already know about what is a stack. First in, first out, right? So whichever is on the top of the stack, that will be popped out. So the instruction push will push the word which is present at a particular address location of the memory onto the top of the stack, and that stack pointer will be updated automatically. And this particular similarly pop, the pop instruction pops the item which is present on the top of the stack. And this particular stack organization, it doesn't require any fields, address field, because the operation is performed on only on the two items which are present on the top of the stack with the help of push and pop operations. So next, coming to the instruction formats. So depending upon the type of CPU organization the processor implements, and depending upon the multiple address fields that are present in the address part of a particular instruction, the instructions are classified into four types: zero address instructions, one address instructions, two address instructions, and three address instructions. And the operations that are specified by the computer instruction they will be executed on the data which can be stored in either the memory locations or in the processor registers. So that is implemented with all the types of instruction formats. So in this video, we'll look at the first type of an address instruction, zero address instruction. The remaining we'll cover it in the next part of the topic. So if you consider a CPU with 16 processor registers, R0 to R15 are present in the CPU, the address of a particular register is mentioned with the help of a 4 bits. So starting from 0000 to 1111. So for example, if you take a binary number 0011, that is nothing but it designates the register R3. So if you are giving the address, in the address part the value as 0011, as we know the instruction format is in a binary format. So whenever your address part contains a value 0011, the CPU will consider that the operand is present in the register R3. So that is how it recognizes a particular register. So coming to the first type of an instruction format, which is a zero address instruction. So this particular instruction does not have an operand field, and the location of the operand is implicitly represented. So this type of computer zero address instruction is represented in the computers which implement stack organization. So all the operations are performed on the stack using push and pop operations. So they doesn't require an operand field because they are performed on using push and pop operations, and operation is performed on the items which are placed, two items which are placed at the top of the stack. So, we'll see an example how to convert an arithmetic expression into a postfix notation, and then we'll convert it into a zero address format. So in this I'm considering this example, the arithmetic expression x is equals to a plus b into c plus d. So this particular expression has to be converted first into a postfix notation. So before converting it to a postfix notation, there are certain rules that you need to follow for converting infix to postfix format. So initially, the operands in the particular expression are represented as A, B, C. So whatever are the operands, A, B, C, the particular alphabets, they are said to be called as operands in your expression. Coming to operators, so the arithmetic operators such as plus, minus, into, divided by, even the open parenthesis, close parenthesis, these are also considered as operators. So coming to the rules, there are mainly three rules that we need to follow for converting an infix expression to postfix expression. So what is infix expression? Whenever an operator is placed between two operands, which means A plus B, we call it as an infix expression. So our example is in the form of an infix expression. So we need to convert it into a postfix. Postfix means that first operand comes, then only the operator. Right? A plus B can be represented as AB plus. So this is a postfix expression. We need to convert our entire expression into a postfix format. So there are three rules mainly. The first rule is the priorities of the operators. So we know that in our expression there are certain operators present. So which operator is having a highest priority and which is having the lowest priority? We need to know that first. So if you consider this, the highest priority operators are multiplication and division. These are considered to be the high priority operators. Coming to a lowest priority, addition and subtraction operators. We call them as the lowest priority operators. The rule 2 is that no two operators of same priority can stay together in a stack column. As we know that this type of zero address format, they work on a stack. So you cannot place the two priorities of the same, two operators of the same priority in a stack together. That is the second rule. Third rule is that the lowest priority operator cannot be placed before the highest priority operator, because the high priority operator cannot tolerate the low priority operator to be placed above it. So lowest priority if you want to place a low priority operator in the stack column, you have to pop the high priority operator which is uh, below the low priority, and then you can place the low priority operator. So that is the third rule. So these three rules has to be followed when you convert an infix expression to postfix expression. Now let us see an example of this. So the same expression x is equal to a plus b into c plus d. So the expression has to be evaluated and the result has to be stored in memory location x. Okay, this is the memory location m of x. So here I have three columns: symbol, stack, and postfix. So whenever an operand is encountered in an expression, you have to place it into the postfix side. And whenever there is an operator encountered in the expression, you have to push it into the stack. This is a rule that you have to follow. So we'll start with the expression. We'll start from here, open parenthesis. So all the symbols will be written here. Whatever you read from this expression, the symbols column, we have to write that. So open parenthesis. So it has to, since this is an operator, it has to be pushed into the stack. So here you don't have anything. Next, A. So A is an operand. So whenever there is an operand, you should not push it into the stack. You have to write it in the postfix column. So the same open parenthesis will be in the stack column. Operand has to be written. Next, the operator plus. So plus you have to push it into the stack. So first the open parenthesis, now plus will be pushed into the stack. A here. Next, B. So B is an operand. So you have to write it here, and the stack column contains the same values. Next, closed parenthesis. So whenever a closed whenever there is an operator which comes between open parenthesis and a closed parenthesis, so what happens when you place this closed parenthesis inside the stack? Then you get an operator plus which is placed between the two parentheses. In that case, you need to pop out the operator. So we're popping out the operator and writing it as AB plus. Okay. Now the stack column is empty. Next, into. So into, it is an operator, so it has to be pushed into the stack. And this column remains the same. And next, open parenthesis. So it has to be again pushed into the stack. Into, next, open parenthesis. This remains the same. Next, operand C. So since it is an operand, you have to write it here. AB plus C. And stack column remains the same. Next, plus operator. So it has to be pushed into the stack. So AB plus C. Next, the operand D. So since this is an operand, you will write it in the postfix column. AB plus CD. Okay. Next, close parenthesis. I am writing it here. Close parenthesis is a symbol, and since when you have close parenthesis, this operator plus comes between the open parenthesis and the close parenthesis. So I popped out. So it becomes AB plus CD plus, and stack column contains only multiplication. Now that should also be popped out at the end. So AB plus CD plus into. So this is a postfix conversion for the infix expression. Okay, this is how we convert an infix expression to a postfix expression. Now we can write it in a zero address format. So this is a postfix expression. So by looking at this, you can simply write the zero address format using push and pop instructions. Push A, push B, next plus operator. So add, push C, push D, add, and multiply. Mul is an instruction. Finally, you have to pop. So whatever the top of the stack now contains the result that will be popped and placed into a location X. Since we have to place it into X. So M of X, the memory address of X contains whatever value is there on the top of the stack, the result. So this is how you can represent an expression into a zero address format. We'll see the remaining types of instruction formats in the next part. Thank you.